I believe you can hear me clearly. So, let's start today's class. Okay. So, okay, so I will briefly review what we learned in the previous class. So, what did we learn? So we learned about basic logic gate of digital logic design. So then, what are logic gates? So actually, for logic gate, so you need to memorize because actually we define the function of a basic logic gate, and then that's just a function. So you need to memorize main function, which means that so this logic gate. So I explained that logic gate or logic gate works like a black box. Okay, well, in this black box, there are one or multiple inputs. Then these inputs are digital signals, and then logic gate generate output signal from these inputs. Okay, and then we also need to define the function of a logic gate, and then based on the function, and logic gate generate the output signal. So, and then also this output signal is a digital signal, right? So we learned about the basic logic gate, like the inverter, the inversion. So NOT gate, it's called a NOT gate. Also, it is called an inverter. Okay? Inverter. And then we learned about the AND, OR, and NOR functions. Okay. And then we also learned about the multi-input logic gate, but it's the extension version of the basic logic gate. So if you understand the basic function of basic logic gate, like the AND function, OR function, then the function, OR function, also exclusive OR and NOT. Actually, there are several basic logic gates, so I think it's not difficult to memorize the basic functions of a basic logic gate. So don't forget checking your attendance on the blackboard. It's a self-attendance, so we are using a self-attendance check system. So you need to memorize this basic logic gate. Okay. Okay, so also we learned about the logic levels. So actually, we are learning about the digital logic system, but I mentioned that our real world handles the analog signals. Also, digital systems also actually handle analog signals, but we just translate the analog signal levels into the digital signals, so digital values such as 0 and 1. Okay, so the ground means the 0 volt of the electric circuit. So we translate ground or near ground signals are zeros of the digital signals. Also, we translate the VDD is the high voltage, and then also we translate the VDD or their VDD voltages are 1. Okay. So I also showed this waveform. As you can see, the waveform is not clear, right? Because of noise signals. So we can see the fluctuations in this waveform. So because of noise signals. So actually, the electric systems handle very nasty very nasty signal, nasty analog signals. But we just translate this nasty signal into the clear digital signals. Okay. So I also explained about the noise margin. So this is just the constraint. It's similar to the specification of a system. So if we design a certain system, we need to consider the constraints of the system. So which means that we learned about the output characteristics of this driver and then input characteristics of the receiver. And as you can see, these drivers and receivers are buffers. Okay. So output constraint define the allowable output signal range, the voltage range. So which means that when the output signal is generated by this driver, then signal one should be the range of this high output range. Okay. Also, the signal value 0 need to be within this low output range. And then also we need to define the input constraint. So as you can see, this input range is wider than the output range. Why? Why? Because noise signals can be included in the wire. So as you can see the wire between driver and the receiver. So noise signals can be included. So which means that it will distort the output level of this driver. So this blue color region represent the allowable input signal range for this receiver. Okay. Then the difference between this output constraint, the output signal range, and the input signal allowable input signal range is defined as the noise margin. Okay. So we frequently use the terminology margin, right? It's some allowable range. So, and then also we define if the signal were some signal. If signals are within the allowable margin, then we can say that our system can work properly. Okay. So I think these parts may be a little bit tricky because we are learning about some analog aspect of the digital systems. Okay, but you need to understand that our digital signal, what is hardware, hardware of the computer system actually work in the real world. So which means that actually these signals and the analog continuous and then very noisy signals. But it just translates the noisy signals like the clear digital signal. So if you are learning about the hardware system, so you need to understand how hardware systems handle these real signals. Okay, so actually I skipped this part, so I explain about the characteristics of the ideal buffer and then real buffer. So what is the buffer? This is the it's not working. broken. Okay, so I will use my finger. So, so what is the buffer? So we take it to work. So what is the buffer? I can use, I cannot use my finger. Oh, unfortunately. Okay, so this is the buffer. Oh, it doesn't work. Okay, I will. Oh, it doesn't work. Okay, so why do we need to use buffer in the circuit? So I said that, so actually, the buffer receives the analog voltage signals, and then actually these signals are analog signals, but we translate these these analog signals into the digital signals. So what is the function of the buffer? If 0 is input, then the buffer generates 0. And then if the signal 1 is received, then buffer generates signal 1, but clear signal. Okay. So this is the characteristics. So DC it is called DC transfer characteristics. So in this graph, the x-axis represents the voltage level of input signal, and then y-axis represents the voltage level of output signals. So let's see the characteristics of the ideal buffer. So how can we translate this graph? Right. Okay. I try to use the mouse. So this is the input voltage level. So if we see that this input voltage level, then from the voltage level 0 to and half VDD, then what is the output signal? Output signal becomes 0. Okay, and then from the half VDD to the VDD, then what is the output signal? The output signal value is the VDD. So how can we translate? So input signal is the range of 0 to half VDD. Then this buffer generates just clear 0 volt signal. And then if the input signal is in the VDD, half VDD to the VDD, then this buffer generates the clear 1 signal, the VDD signal. So this is the ideal buffer. But ideal is so it's a fantastic buffer. So it's not real. So actually this graph shows the DC characteristics of real buffer. So what can we observe? So as you can see, so the output value changes continuously until 0 to VIL. Okay, so actually you can think that this is around the half of VDD, but before the input signal, which is the half of VDD, we can observe that output signal also increases, right? So and then after this VIL, the output signal increases dramatically, but it linearly increases. In this ideal buffer graph, so you can see that this voltage level is orthogonal to the x-axis, right? But as you can see, so this voltage level, output voltage level increases linearly. It's not orthogonal to the x-axis, right? And then, as you can see, also from the VIH sheet, the output signal is slowly increases and then it will saturate. So what can we observe? So in this real basic characteristics of real buffer, we can define the BIL and then BOL, then BOH, then BIH. So we assume that if the input signal is in the range of is 0 to BIL, the output voltage level is slightly increases, but we allow that. So we assume that this buffer is tolerable until this BOL level. Okay, so which means that this buffer can generate around about the voltage level within this range. Okay, if the input voltage level is in the 0 to VIL, and then actually it's ranging. As you can see, we assume that real buffer works like this. Okay, but not the ideal buffer, the unreal buffer. So ideal buffer works like this. It's orthogonal to the x-axis. But as you can see, you can observe the flow. So this range, the buffer will not work properly. Okay. Then also this high level ranging is the same. So actually for the ideal buffer, noise margin is the half VDD. Okay, so this is the output range, the generated output value of the ideal buffer. But as you can see, the ideal buffer is tolerable, so which means that ideal buffer will generate the ideal value if the input is until the 0 to VDD, the ideal 0. It will generate the ideal 0. But in the real buffer, so this voltage level increases slightly, so we just measure this slope of this graph. Then if the slope is 1, then we just decide this x-axis value is the VIL, and then y-axis is the VOL. And then we assume that the voltage, this buffer works properly within this range. So actually the noise margin is less than the VDD. The noise margin is smaller than the VDD, half of VDD. So let's see the supply voltage of the digital circuit. So I frequently use the terminology VDD. So this is it is called a supply voltage. So if we are interested in the electric circuit, then you can find that the electric circuit is connected to the VDD and ground. And then actually this circuit, the electric circuits work within this range, the ground to VDD. Actually the VDD decides the high voltage of the installed circuit. Okay. In 1970s and 1980s, the VDD was 5 volt. And then recently it's the CPUs. The modern CPUs use 1 volt, 1.0 volt as the supply voltage. So which means that the supply voltage is decreased continuously. Okay. Then so what is the benefit of this voltage scaling? So we can reduce the supply voltage level of our circuit. If we use the barrel transistor, so which means that I explain about the technology node of the semiconductor technology, and then I mentioned that recently we are using 5 nanometer technology. So this is very, very small. So and then 5 nanometer represent the channel width of the transistor. So if we use a smaller transistor, then we can reduce the supply voltage. So we can save our consumption of the digital circuit. Okay. So think like this. So the voltage level is the 5 volt, and then the power. What is the power? So what is the power? The power. Okay. What is the power? Power is the current multiplied by voltage. So it is proportional to the B, the supply voltage. So which means that if we reduce supply voltage, we can reduce power consumption of the circuit. So, and then currently we are using 1.0 volt as the supply voltage of the CPU. Okay. So, and then actually we need to provide the proper supply voltage to the electric circuit. Right? If we just provide the higher supply voltage to the electric circuit, then the electric circuit will be broken. Okay, so this is just a joke. The chips operate because they contain magic smoke. So it's a joke. It's not a real fact. Why? Because if we just provide the higher voltage level to the CPU was intelligent circuit, then it will be burned. So which means that it will be broken. And then because we just provide the higher voltage level, then the CPU is burned and it generates the smoke. And then if the smoke is generated, the circuit is really broken, then we cannot use the electric circuit. So this is the photo of the AMD CPU. Okay, as you can see, if we provide the higher voltage level and higher supply voltage, and it is on. Okay. So we need to provide the proper voltage level. Okay. Let's move on to the transistor. So I think this part is a little bit tricky because we will learn about the basic properties of transistor. So actually, as I mentioned, we can build digital systems using transistors, and then actually the basic logic gates are built from transistors. So if you can, so and then so recently many people say the semiconductor industry is very, very important. Okay, and then the United States and then China, also the South Korea, are focusing on the semiconductor industry. So it's very important for the industry of nations. Then, even though I believe most of you are interested in computer software and computer science and engineering, but if you can understand how the transistor works, then it will be very helpful. So you can understand how real hardware, a real digital system work with the basic operation property of CMOS transistors. Okay. So now, we will learn about the basic characteristics of CMOS transistors. But don't worry, I will not teach the difficult properties of the transistors. I just explained the basic properties. Okay, so it's a simplified, so it's the kind of abstraction, the abstracted level of the transistors. Okay, then what are transistors? So this is the definition of a transistor. Then I just copied this definition from Wikipedia. Then what can you see? So what is a transistor? It's a semiconductor device. Okay, as I mentioned, everyone knows. Then why do we use a transistor to build electric circuits or electric systems? Transistor can be used for amplification, or switch. A transistor can be used as switching or amplifiers. But so this amplifying is the kind of analog circuit. So we can build analog circuits, they can amplify input signals. So we will not learn about this property of the transistor, but for the digital circuit, we use the switch. So what is a switching? The switching operation of the transistor. So for the digital circuit, we exploit the switch-like operation of the transistor. And what is a switch? What is a switch? Like these switches. So if we can use switches for turning on or turning off device, right? So if we just turn on the switch, the device is working. And if we just turn off the switch, then the device is not working. The transistor works like this. Actually, you can understand a transistor is a controllable switch. Okay, it's a controllable switch. So what does that mean? Actually, a transistor has a 3-node, and then we can just control the turn on or turning on or turning off these 2 nodes using this control knob of the transistor. Okay. So if we can understand the switch-like operation of the transistor, then you can easily understand why we build these logics using CMOS transistors. Okay. You can understand a transistor like this figure. So this figure shows the symbol of a transistor. So as I mentioned, the transistor has 3 nodes here and here and here. Okay, transistor has 3 nodes. And then what is a node? So node is connected to the outer world. So which means that we can just connect some signals into these nodes. Okay. So these nodes are called the drain. So that's why I use D for this node. And then this node is called a source. Okay, the drain. Source. Then this node is called a gate. So, and then this figure shows the operation of a transistor. Actually, this D represents this D node is a drain node. Then this S represents this node as source node. And where is G? 8. The gate is here. G equals 0 and G equals 1. You can just understand this property, the working property of the transistor. And what is it? If G equals 0, okay, if the gate voltage level is 0, so which means that the voltage level of this gate node is low. Okay, then what is this? So D is connected with S, so which means it's disconnected, so it's turned off. Okay, good. The wire is disconnected, then the current cannot flow through this wire. Okay, this is turned off. If drink one, so we just provide high voltage to the gate node, then you can observe the D is connected to S. So which means that the current can flow through this wire. So this is turned on. So this is the basic operation of a transistor. So which means based on the gate level, gate voltage level, that we can turn on or we can turn off this transistor. So which means that the drain can be connected with source or instead of disconnected. The drain can be disconnected with source or drain can be connected with source based on the gate signal. The voltage level provided to the gate. So you can just understand this property, okay? So and then so you can just learn the common sense of the transistor. So you can think that it's just the common sense. Okay, so we can build transistor using silicon. So actually silicon has the property of semiconductor. So what is a conductor? The conductor means that conductor includes many free electrons, then the current, electric current can flow via conductors. Okay, so conducting materials. So for example, if we use a copper wire, okay, then we know the electric current can flow through the copper wire. So 전선, 우리 전선 말하는 거예요. Then you can say that this is a conductor. Okay, the conductor means that the conductor includes the many free charge, so which means many free electron. The electric current can flow via a conductor. But the silicon is called a semiconductor, which semi means the half. So it's half conductor. So because as you can see, you can build the transistor or semiconductor devices using the silicon. So silicon is the base material of semiconductor material. So as you can see, the silicon can be connected to each other. The silicon elements can be connected to each other. But if the silicon elements are connected to each other, we cannot find enough free electrons. Okay? Because the silicons are tightly connected to each other, and then actually the silicon has the outer orbit of the silicon element. Yeah, silicon has only 4 electrons, and then as you can see, the silicons are connected in 4 directions. Okay, so actually the 4 free electrons are used for connecting each other. It is a kind of chemistry analysis. So, but you know, silicon is a 4 conductor because we cannot find enough free electrons. Okay, but if we just include the other materials such as the arsenic, so or boron, so arsenic has the 5 electrons in the outer orbit of the element. Then boron has 3 electrons on the outer orbit of the element. Okay, so if we just include other material on the silicon, then we can make different type of material. So this type is called the N-type material, and then this type is called the P-type material. So actually, as I mentioned, the arsenic includes the 5 electrons, so it's an additional 1 electron. So if we just include the arsenic on the silicon material, then we can make the N-type material. So this N-type material has many free electrons, so it has the different property compared to the pure silicon. Then P-type has the less free electrons. So actually, we can say that the P-type material has holes. It's a kind of plus charge element. Okay, so the P-type has many holes. It's kind of so P-type has the plus charged element. Okay, and then so it's a little bit tricky, right? So because not to understand some basic property of the semiconductor and the P-type or N-type elements, then we need to understand the basic knowledge of the chemistry and then also the material science. Okay, but first remember that pure silicon does not include the enough free electrons, but if we just include that, this is called doping. DOPE, so doping. So if we dope with the other material, other elements, we can make the different types of material in the silicon. Okay, N-type material and P-type material. And then by combining these N-type and P-type silicon, then we can generate MOS transistor. So MOS transistor represents the metal oxide silicon because we can. So it's actually this terminology is very straightforward. So it means that we can build transistor using this metal layer and then silicon dioxide. So that's why this transistor is called MOS transistor, metal oxide silicon. Okay, let's see. So this figure shows the figure of NMOS transistor. Okay, and then this is the symbol of actually NMOS transistor. Actually, I showed this symbol in the previous slides, right? So as you can see, this is the gate, this is the source, this is drain. MOS transistor has 3 gates. Then I also explained the basic property of this transistor. So as you can see, this is the figure of the NMOS transistor. You can find the N-type silicon here, and then P-type silicon here. Okay, and then this is the source, this is the drain, and then this is the gate. So actually, the metal wire is connected to this N-type silicon. So this is called the N-well. Okay, well, the N-well. And then the polysilicon is called is doped on this layer, and then actually we just generate the silicon dioxide layer, the polysilicon layer, and then SiO2 is the pure conductor. So which means that actually the current cannot flow through this layer. Okay. So I'll briefly explain how does it most transistor works. So as I mentioned, the growth actually is called the substrate. This substrate is connected to the ground always. Okay, and then the transistor, NMOS transistor has a three gates, then source and drain, and then the ground, the gate. Let us assume that the gate is connected to the ground. Okay, then what will happen? So actually there are many free electrons here, so in the N well, but as I mentioned, the P type silicon includes holes. Actually, the electron cannot transport from this side to this side because there is a P type silicon here. So even though the N type silicon includes the many free electrons, but these electrons cannot transfer from this side to this side. And then let us assume that the ground is connected to the gate. So if the ground is connected, then what is the voltage level between this substrate to the gate? Okay? So ground and ground. So there is no voltage difference, right? Right? So it's a kind of physics, electric physics. So because we cannot observe differences in the voltage level between gate and substrate, then the electrons, the channel is not generated here between the source and drain, which means that the source and drain is connected. But if the one VDD is connected to the gate, what will happen? So substrate is connected to the ground. So this is the high voltage level, and then this is the ground level. So we can observe the voltage difference between gate and substrate. If we can observe the high voltage here, then this area becomes the high voltage. So plus we can observe the plus charge here. So which means if the plus charge, then and then also I mentioned that this is the poor conductor. So which means that the electrons cannot move through this layer, but we can observe the high plus charge this side. So what will happen? Actually, the electrons are gathered under this layer, silicon dioxide layer. So which means that free electrons gathers under this layer. So which means the channel is generated. So what is the channel? So which means that this N well is connected to other side N well via this channel. So I mentioned that, or I frequently mention a channel width. So width represents the distance between this NL and then this NL. So if the channel is generated by the free electron, then the free electrons from this node to this node, the electron can go from this node to this node because the channel is generated. Okay, it's connected, and the current flow from this node to this node. That's the basic operation of the transistor. So actually, the real operation is more difficult, is more complex than this brief explanation. But you can just understand how transistor works like this. Okay, you can just remember that channel can be generated if we just provide the high voltage to the gate, the NMOS transistor. And if just the gate is connected to the ground with the 0 volt, the channel is not generated, it's connected. Okay, it's connected. So which means that using the gate voltage level, that we can just control the operation of the transistor. And then actually there are different types of transistor called the CMOS transistor. So actually I explained about the NMOS transistor here. So you can see the title of the slide. But the PMOS is actually PMOS has the opposite characteristics. Okay. So the P well is here, and then you can find the N substrate, N type substrate. And then this is the symbol of PMOS transistor. Okay. So what is different? If we just see the PMOS symbol of the PMOS transistor, what is different? Only difference is 뭐죠? Different point is the bubble. And then I explained that in a digital circuit, bubble represent what is the bubble? Bubble represent inversion, right? Right. So actually, when we learned about the NMOS transistor, I explained that the channel is generated if the gate is connected to the high voltage event, which is the 1. Okay, but PMOS is opposite, so which means because of this bubble, PMOS transistor is turned on if the gate is connected to ground. So if 0 is given to this gate in the digital level, if the 0 is given to the gate, then PMOS transistor is turned off. Then on the other hand, if the 1 is given to the gate node, then the PMOS transistor is turned on. So this is different. The NMOS transistor, so this is the symbol of the NMOS transistor. Okay, so if the 0 is given, then the circuit is turned off, the switch is turned off. But if the 1 is given to the gate, then this switch is turned on. Okay, this is the NMOS transistor, and then this is the symbol of NMOS transistor. You can understand the operation of an NMOS transistor like this. And then, as I mentioned, the PMOS transistor includes the bubble, so which means inverse. So the PMOS is the gate, so 0 is given to the gate node turned on. And then if the 1 is given to the gate node, it's turned off. Okay, it's a summary of the transistor function. So it's a symbol, and then the gate is 0, then NMOS is turned off, but the PMOS is turned on. So this is a difference. So the bubble means the inverter. Okay, so if the gate is 1, the turned on, the NMOS transistor is turned on, and then PMOS transistor is turned off. And then we can actually build electric circuits using NMOS transistor and PMOS transistors. So that's why these transistors are CMOS transistor. C means the complementary. So I cannot write, unfortunately, the complementary. So by combining PMOS transistors and NMOS transistors, then we can build basic digital logic. Okay, so as you can see, the PMOS transistors are connected to the VDD, and then NMOS transistors are connected to the ground, and then other node, the other node of the PMOS and NMOS transistor is connected to the output common. Also, input signals are connected to the gate node of the PMOS and NMOS transistor. Why? With the input signal, with the gate node signals, we can control the operation of operation. Operation is just turning on or turning off. So we can control the operation of these transistors. So which means that the input is given to the gate node of the PMOS and NMOS transistors, so we can control the output. Right. So when I explain about the basic gates, so basic gates includes the input signals and then output signals, right? So then based on the defined function of the basic gate, and the input signal is given, then output signal value is changing. Right. So using transistors, the gate is connected to the input. So input signal is changing, then operation of transistors are also changing. So we can build basic gate using the registers, NMOS and CMOS transistors. Okay, let's see the operation of NOT gate. So in the previous class, we learned about the NOT gate, right? So this is NOT gate, so you can see the bubble here. And then you can see if we use the bar here, and this is NOT gate, and this is A is input, and then Y is the output of the NOT gate. And then we can build NOT gate using transistors like this. We can observe PMOS transistor here is the P1, and then also we can observe NMOS transistor here. And then, you know, the Y is on output and A is on input. And then based on the input signal, then output signal is generated like this. Okay. Then let's see the operation of the transistors P1 and N1. So you can see the P1 and N1 here. And then if the input is the 0, so which means A is connected to the ground, then what is the operation of the P1? Each on the transistor P1 is turned on, right? Because the 0, then you know bubble means the inverse. So P1 is turned on. And then if the 0 is given to the gate node of the NMOS transistor, it's off. So then what will happen? So in this situation, the P actually is the VDD, okay? And then PMOS transistor is connected to the VDD, right? And then NMOS transistor is the grounded, is disconnected. And then this is the output, the Y. So Y is connected to the VDD, okay? The VDD, so Y is high, the VDD, so it's 1, right? Easy, it's easy, right? Okay, so based on the basic operation, the switch-like operation of the transistor, then we can build the basic gate like this. So using by combining PMOS and NMOS transistor, if the A is 0, then output becomes the 1. And then if the A is 1, the high voltage, then it's inversely off. and then NMOS transistor is on, then what will happen? In this case, the Y is disconnected from the output is disconnected from the VDD, and then Y is connected to the ground. So Y is low, is the 0. Right. So it starts from these basic properties of most transistors. So based on the very simple, actually, I think, but I believe the basic switching operation of most transistors is very simple. It's controllable switch, and then by combining two different controllable switches, like the PMOS transistors and NMOS transistors, we can build basic gates. This is the example of NOT gate. So this is the inverter. Okay. We can also build NAND gate also. Okay, so this is the truth. So this is the symbol of the NAND gate, and then so this is the truth table of the NAND gate. So the NAND gate includes the two inputs and then one output. And then based on the input signal levels, the output signals are generated like this. So, and then this is the circuits of the NMOS transistor. So we can build NAND gate. Sorry. So this figure is the NAND gate of the this is the circuit of NAND gate. Sorry about that. So we can build our NAND gate using two PMOS transistors and then two NMOS transistors. Then the PMOS transistors are organized in parallel, and then NMOS transistors are connected to ground in stereo. Then actually the NMOS NAND gate has the four different inputs like 0, 0, 0, 1, 1, 0, and 1, 1. And then if we can figure out the operation of these different four transistors, then we can also figure out the output level. So let's see that this first case, 0 and 0. So the A input is connected to the gate node of the PMOS transistors and the NMOS transistors. Then all input signals are 0. It's ground. Then P1 is on, right? On. It's on. It's off. It's off. So NMOS transistors are connected to the ground, but these two NMOS transistors are turned off. Okay, so which means that the Y is connected from ground. And then because the two PMOS transistors are turned on, the Y is connected to the VDD. So which is Y is 1. How about the 0, 1? The P1 is on, right? And then P2 is off. And then P and 1 is off. Okay. Sorry about that writing. And 2 is on. So what will happen? So the PMOS transistors are connected in parallel, connected to the VDD in parallel. So which means that if one of PMOS transistors is turned on, then Y is connected to the VDD. Okay, understand? So in this case, the Y is connected to the VDD, but the NMOS transistors are connected in serially. So if the one of its NMOS transistor is connected to the ground, then this Y is connected from ground, right? Because the NMOS transistors are connected serially. So what will happen? So Y is disconnected from ground in this case, then Y is connected to the VDD. So this is 1. And this is the same. So if we just use the 1, 0, it's off, on, off. Okay. So this is 1. So Y is disconnected to the from ground, and Y is connected from VDD. How about the 1, 1? So PMOS transistors are all turned off. It's off. And then NMOS transistors are all turned on. So Y is connected to the ground, then Y is disconnected from VDD. So this is 0. So if we see the value of the Y based on the operation of most transistors, then we can observe that this value, this level is same to this truth table, the contents of the truth table. Okay? So we can build named gates using most transistors like this. Okay? So as you can see, so if I show the 2 examples of digital logic. So not gate and NAND gate. And as you can see, the PMOS transistors are connected to the VDD, and then NMOS transistors are connected to the ground. And then actually the PMOS and NMOS transistors share the same output. Okay, so the source gates are commonly connected to the output signal, and then input signals are connected to the gate of most transistors. Then we can build the 3-input NOR gate like this. So we can build the 3-input NOR gate like this. Okay. So as you can see, the PMOS transistors are serially connected to the VDD, and then NMOS transistors are connected to the ground in parallel. Okay. Then how can we build 2-input AND gate? So we learned about the 2-input NAND gate. Then how can we build 2-input AND gate? Can you guess? So you know, I showed the example of NOT gate. I showed the example of AND gate. Also, NOR gate, 3-input NOR gate. Then what are the common parts of the NOT gate, AND gate, and NOR gate? What are the common parts? Common part is bubble. Okay, so actually NAND gate, NOT gate, NOR gate includes bubble. Okay, commonly, right? And then we can actually straightforwardly build is NOT gate, NAND gate, NOR gate using CMOS transistors. And why do I explain this? So now how can we build the AND gate? Actually, so the AND gate does not include a bubble, right? We need to build AND gate like this. So we cannot directly build AND gate from basic MOS transistors. So actually we need to combine two logic gates. So we first need to build NAND gate using CMOS transistors, and then the output of NAND gate is connected to the inverter. So that gate. So why do I explain this? Actually, we can easily, straightforwardly build NOT gate, NAND gate, and NOR gate using CMOS transistor, because the MOS transistor. So you know the gate is directly connected to input signal without a bubble. Okay, but you know the MOS transistor is connected to the ground. The ground means 0. So actually we can control the connection and disconnection of ground using MOS transistor. MOS transistor does not include a bubble. So which means we can easily build NOT gate, NOR gate, NAND gate using these CMOS transistors. But in order to implement AND gate or OR gate, okay, then we need to combine NAND gate and inverter, or NOR gate plus inverter. Okay. Then, why do I explain this? It is related to the cost of hardware. Understand? So actually, these most transistors are kind of hardware resources, right? So we need to actually draw the layout of the most transistors. So and then also the transistors occupy area of chip. Okay. So actually the hardware costs are determined by number of transistors. Also the power consumption and some other parts are also determined by number of transistors. So you can think that the hardware cost, the cost of hardware system is determined by number of transistors. So, which means in order to implement NAND gate, we require total 4 transistors, right? But in order to implement AND gate, we require total 6 transistors, right? We require the 4 transistors for implementing NAND gate. Then we require additional 2 transistors for implementing NOT gate. So actually, in order to build AND gate or OR gate, we require 6 transistors. So just compare the other resources, then the AND gate require 1.5 times of NAND gate. Okay, so 6 and 4. Okay, so there are different kind of gate. So it's called the transmission gate. So it's just a switch. So if we see the transmission gate, then so this is the gate. The NMOS transistor is here, okay, and then this is the PMOS transistor, and then the gate is connected to the control signal EN. EN means the enable signal. So and then A and B are connected. Then what is the operation of this transmission gate? So EN is the control signal. So based on the control signal value, so A can be connected with B, or A is disconnected from B. You understand? So if the EN is 1, then A is connected, because you can see the bar here, which means it's the inverse of enable signal. So if this is 1, then EN bar is the 0. So 0 is connected to PMOS gate. So A is connected to the B. On the other hand, if the EN is 0, then A is disconnected from B. So by combining NMOS and PMOS transistor, then we can build the transmission gate. But you may think, oh, why do we need the two different types of transistors? Because I already explained that transistor is the controllable switch. So basically, a transistor is a switch. But in order to build the switch, so this is also the switch, right? The connected or disconnected based on the enable signal. But we need to combine PMOS transistor and NMOS transistor. It is because of the electric characteristics of a transistor. So as you can see, NMOS has one signal, the high voltage signal, forward. Then PMOS transistor has this low voltage signal, forward. So which means that if this signal is 0, and if we just use the PMOS here, not NMOS, then it can be connected, but it includes the very nasty signal. It's not clear. We cannot pass the 0 to E clearly. We cannot pass 0 to E clearly. Cannot. Okay? It is because of also the property of PMOS transistor. And also that's why, so you know, in the CMOS transistor circuit, the PMOS is only connected to the VDD. It is because PMOS can pass one clearly, but PMOS cannot pass 0 signal clearly. That's why the PMOS transistor is only connected to the VDD. Then NMOS transistor, inversely, the NMOS transistor is connected to ground. So, in order to implement a controllable switch, because of the electric characteristics of the MOS transistor, we need to combine NMOS transistor and PMOS transistor. And then this gate is called the transmission gate. Okay? Transmission gate is just a controllable switch. Okay? It's a different. So in the previous class, we learned about the basic gate, NOT gate, AND gate, OR gate, and the exclusive one. Okay? But this is another type of gate, the transmission gate. And then transmission gate, the people enable is 1, and switch is on, and then enable is 0, and then switch is on. Okay? Okay, so I will stop here. Okay, so in the next class, I will explain about the power consumption. Okay, and sorry about the information. Okay, any questions? Okay, I'll see you in the next class. 감사합니다.